Watch this. The motor is running normally. Then a warning alarm appears on the screen and after a while, an overload happens. Instantly, the operator sees a red alarm on the HMI. So instead of guessing what went wrong, they can see the fault, understand the reason, and react quickly. That's exactly why a good alarm system is so important. When something important happens, the operator should know what happened, why it matters, and what needs attention. So the question is, how do you build that kind of professional alarm management in TIA Portal? How do you make the HMI show the right message with the right priority and let the operator handle the alarm correctly? That's what I'm going to show you in this video. Step by step, we'll build real HMI alarms in WinCC using a practical motor example. We'll create overload and emergency stop alarms, add a temperature alarm, organize them properly, and display them on a working alarm screen. So by the end of the video, you'll have something that looks and works much more like a real machine. An HMI alarm is a message that tells the operator that something important needs attention. It could be a fault, a warning, or a process value that has moved outside the normal range. So how do we build a proper alarm management system in TIA Portal? Because a real alarm system is more than just one red message on the screen. First, you need alarms that appears at the right time. Then you need to show them clearly to the operator. After that, you need a history of what happened before, not only what is active right now. And finally, you need the right operator actions like acknowledge, silence, reset, and later also a buzzer. That's why I made this as a 3-part series. In this first video, we'll build the foundation. We'll create the alarms for our motor example, decide which ones should be warnings and which ones should be fault, place them on an HMI alarm screen, and test them live. In the second video, we'll go one step further, because in a real machine, the operator also needs to see what happened earlier, not only what is happening right now. So there we build the alarm history screen, login and filters, and we'll also look at other types of alarms so the operator can quickly check past alarms and understand the sequence of events. Then in the third video, we'll make the whole system behave more like a real machine. We'll add the buzzer and the operator actions like acknowledge, silence, and reset, so the operator can respond properly when a fault happens without the system becoming annoying or confusing. So in this video, we start with the first and most important step, how to create the alarms correctly and show them clearly on the HMI. I've already created a project in TIA Portal with one PLC and one HMI connected. On the PLC side, I'm using an FC for the motor example. That FC is being called from a cyclic interrupt OB with a cycle time of 700 milliseconds. I'm also using a data block called DB motor. Inside the DB, I have the command bits start, stop, and reset. These are used to control the motor from the HMI. Then I have stop, which simulates an emergency stop condition. Motor on, which tells us if the motor is running. Motor overload, which simulates an overload fault. And motor temperature, which gives us the actual motor temperature value. When I press start and there is no stop and no overload fault, the motor starts running. When I press stop, the motor turns off. And if stop becomes active, the motor also turns off immediately. If the motor is running, the temperature rises gradually. If the motor is off, the temperature drops gradually again. While the motor is running, I count its runtime. When the counter reaches 40, the motor has been running for 28 seconds. At that point, motor overload becomes true automatically. The motor turns off and the overload alarms appears on the HMI. Reset only works when E-stop is not active and the motor temperature has cooled down to 35 degrees or below. Only then can the overload fault be reset and the motor is started again. Because on a comfort panel we can only use integer or word as the alarm trigger data type, I created one separate word variable for each alarm. When the Boolean condition becomes true, I set the word to 1, so only bit 0 changes. And that's the bit I use as the trigger in the HMI alarm. So with this small piece of code, we already have a small but realistic demo. The motor starts, the temperature rises, a warning appears, then an overload fault happens automatically. And after cooling down, we can reset and run it again. I put this code in the video description so you can use the same setup in your own project. Now the next step is to bring these signals into the HMI. On the HMI side, I already have a main screen for the motor overview and an alarm screen where the alarms will be shown. So now let's move to the HMI alarm configuration. In the project tree, open your HMI device and then go to HMI alarms. This is where we create and organize the alarm messages that the operator will see on the panel. Here you'll usually see different tabs or sections for different alarm types. For this video, we only need the two most important ones, discrete alarms and analog alarms. Discrete alarms are used for signals that are either on or off, like overload or E-stop. Analog alarms are used for values like temperature, pressure, or level. You may also see other alarm-related tabs here depending on your WinCC version, but we'll leave those for later videos and stay focused on the practical basics first. Let's start with the first alarm, motor overload. I'm starting with this one because it is the easiest type to understand. This is a discrete alarm, which means it is based on a signal with two states. In our case, the alarm becomes active when the overload condition becomes true. So I add a new entry. ID is just the internal number of the alarm. Name is the engineering name of the alarm inside the project. Alarm text is the message the operator will see on the HMI. So here I use a clear description like motor overload fault. Alarm class defines how important the alarm is, how it looks, and how it behaves. For now, I use errors as the alarm class. We'll talk about alarm classes in more detail later. Trigger tag is the PLC or HMI tag that activates the alarm. So here I link it to the overload trigger tag. The trigger bit defines which bit of the trigger tag will activate the alarm. In our case, each trigger word changes only between 0 and 1, so only bit 0 changes. That is why I use bit 0 as the trigger bit. Trigger address shows the address behind that trigger signal depending on the tag configuration. Here it shows the first bit of the overload trigger variable inside the DB. Then you see the columns for HMI acknowledgement bit, and HMI acknowledgement address. These are used when an alarm should be acknowledged from the HMI side, for example by an operator or by an acknowledgement tag. And finally, report decides whether this alarm should also be reported or logged, depending on your panel and project setup. The HMI acknowledgement fields and the report option are more advanced settings, and we'll cover them in later videos. For now, I'll leave them unchanged because we don't need them yet for this basic alarm setup. If you look at the properties window, you can also see a summary of the settings we have already defined for this alarm. You can also see the info text field here. This is extra information for the operator. For example, the possible causes of the alarm or what they should check first. For example, I could write something like check motor load and reset after cooling. Now let's add the second alarm for emergency stop. This one works exactly the same way as the overload alarm. So I create another discrete alarm. Enter the alarm text emergency stop active. Choose the alarm class errors and connect the trigger to the eStop alarm word. Again, I use bit 0 as the trigger bit. And for the info text, I can enter something like check the eStop to run the motor again. Now we already have two common discrete alarms, one for motor overload and one for emergency stop. For the temperature alarm, we'll do it differently because temperature is not just on or off. It's a changing value. So for this kind of signal, we use an analog alarm. I add a new analog alarm. For the alarm text, I use something clear like motor temperature high. And for the alarm class, I choose warning because this is not yet a shutdown fault. It's a warning that tells the operator the motor is getting too hot. Here, instead of using a trigger word and the trigger bit, we use the actual process value itself. In our case, that is motor temperature. Now I set the high limit. Here I can enter the value directly as a constant or use an HMI tag to change the limit dynamically. For this example, I entered 45 as the analog alarm limit, and with the limit mode set it to higher. That way, when the motor temperature reaches 45 degrees or more, the HMI will show the temperature warning. So this alarm works differently from the first two. The overload and eStop alarms are triggered by discrete signals, but this one is triggered by a value crossing a limit. And that is exactly the basic difference between discrete alarms and analog alarms in WinCC. Discrete alarms react to a signal state, analog alarms react to a process value reaching a defined limit. Now that the alarms are created, the next step is to show them clearly on the HMI screen. On the main screen, I keep the setup simple. I add the main control buttons like start, stop, reset, and eStop and bind them to their variables. I also show the most important motor information like the motor status, the actual temperature value, and a few simple icons and text for overload and warning. The goal of this screen is just to give the operator a simple overview and a way to control the demo. Now let's move to the alarm screen. This screen shows the alarms themselves. So here I go to the toolbox, open the controls and insert an alarm view onto the screen. Then I resize it so the operator can read the alarms clearly. After inserting the alarm view, let's quickly adjust the most important properties. There are many settings here, but for this video, we only need a few of them. First, under General, I choose what kind of alarm information this view should show. For this first video, I want to show the current alarm states because the main goal here is simple. When a fault or warning happens, the operator should see it immediately on the screen. You can also choose alarm buffer or alarm block. The alarm buffer is more for past alarm events, and the alarm log is for stored alarm history. We'll use those in the next video, so for now I'll leave them out and keep this first screen simple. Next, under display, I have some basic view settings like vertical scrolling, horizontal scrolling, grid, and focus width. For this project, I keep the scrolling enabled because that makes it easier to move through the alarms later. I leave the extra control tag fields empty because we do not need them in this video. After that, under toolbar, I choose which buttons should appear directly in the alarm view. Here I keep the buttons enabled that I want to use in this project. Then under column headers, I define the titles shown at the top of the table. The goal here is simply to keep the headings clear and easy to understand. And under column, I choose which information should actually be visible in the alarm view. For this beginner setup, the most important columns are alarm number, time, alarm status, alarm text, and date. On the right side, I also keep headers enabled so the table titles stay visible. I keep record columns enabled, and I also keep sorting by date and time possible enabled. For the sort order, I choose descending, so the newest alarm appear at the top. The other properties are not important for this video, so I leave them at their default setting. Now the alarm screen is ready and the basic setup is complete. So the next step is to download the project and test everything in runtime. I start the HMI simulation. First I press start. Now the motor starts running and we can see that the temperature begins to rise gradually. As the motor continues to run, the temperature reaches 45 degrees. At that point, the warning condition becomes true and the HMI shows the temperature alarm. The operator can now see that the motor is getting too hot even before a real fault happens. I stop the motor, let it cool, and then start it again. And that is exactly why warnings are useful. They give attention early before the situation becomes more serious. This time I'll let the motor continue running. After a while, the overload condition becomes true. At that moment, the HMI shows the overload alarm and the motor is switched off automatically. Here we can see the alarms with their time and date, so the operator can follow what happened and in which order it happened. We cannot start the motor again until the temperature drops to 35 degrees or below, and then we press the reset button. After pressing reset, the overload fault clears and the motor can be started again. Next, let's also test the emergency stop alarm. I activate e-stop manually and now the HMI shows that emergency stop is active and the motor is stopped. This is another common machine alarm and it is also a fault alarm because it needs immediate attention from the operator. Now you may notice one important difference on the alarm screen. The temperature warning has disappeared while overload and e-stop faults are still there. The temperature warning has disappeared because the temperature dropped below 45 degrees again. So a warning alarm is only visible while the warning condition is present. Once the reason is gone, the warning alarm goes away too. That is one key difference between a warning and a fault. Fault alarms like overload or emergency stops are more serious, so they are handled differently. In the next videos, when we work with history, logging, and acknowledgement, this will become much clearer. Alright, in this video we built the first and most important part of the alarm system. We created 2 discrete alarms for motor overload and emergency stop. We also created 1 analog alarm for motor temperature. Then we placed everything on an HMI alarm screen and tested it live in runtime. So now when something important happens in the process, the operator can already see it clearly on the panel. But maybe now the next question is, how can we store the alarms and see what happens earlier? That's exactly what we'll do in the next video. There we'll build the alarm history view, work with alarm buffer and alarm log, and add filters so operator can find alarm information much faster and with more details. So continue with video 2, because that is where this simple alarm screen starts to become a much more professional alarm system. See you in the next video, friends. Bye.